Our next talk will be by Shane Thompson from ASU, and he'll be talking about new lunar impacts during LRO. And Shane, go ahead and take it away when you're ready.
All right, thank you. Let's see. After 4 years now of LRO orbiting the moon, LROC has been able to collect an extensive data set that we can start searching and looking for new impacts. And as this slide here shows, back in September of 2010, we imaged an area, and then in March of 2012, we imaged it again. And as you can see, there's a pretty nice impact that formed there. The ratio image on the right is between those two, and it clearly identifies the morphology of that impact structure. Next slide. Prior to this study, looking at this kind of activity with recent impacts in the Earth-Moon system have been based on NEOs, meteors in the Earth's atmosphere, monitoring systems such as the European Fireball Network, and events like Kellyevents, Russia. At Mars, they've detected quite a few new craters in the Mach and high-rise data, and I apologize, these references should have et al. Behind them. And at the Moon, NAC data have been compared early in the mission with digitized Apollo panoramic camera data, and they have found 5 craters. And then finally, the Marshall Space Flight Center has obviously been doing the flash monitoring network for the last few years and discovered quite a few flashes. Can't click. Okay, just went ahead. Sorry. Went 2 slides. All right, detecting changes over time. We set out to look at NAC data with older, previously acquired NAC data, and we would target observations with similar lighting conditions on that day's planned flyover. And then we found that looking at images with incidence greater than 70 degrees became very difficult to identify any change detection versus the changing shadows of the scene. And the new observations paired with an old observation are termed a temporal pair. And that's the old left and right matched with a new left and right overlapping the area. And then we went through, processed all that data, spent a lot of time figuring out how to get the map projection and co-registration to reliably and accurately line up. And fortunately, that is now an automated process. And we've begun going through the stage of looking at the data and analyzing it for any of the new impact features that have been found. This slide shows an example of what one of these temporal NAC pairs look like. On the left are the 3 products that we scrutinize over. The new and old products produce the ratio. The ratio is scanned looking for any change detection between the two, and then we analyze it in the image data. The example on the right shows where an impact was found. It's not seen at the tip of the arrow in the old image. In the new image, it's there. And then the ratio image, it stands out like a sore thumb, nothing like anything else in the scene that was undisturbed. In this case, it's we call this a high reflectance change, where the surface albedo has brightened relative to prior to the impact. Sometimes it can be a darkening event. We call that a low reflectance change. And sometimes it's a little bit of both, as in this example that Mark showed on Tuesday. In the upper left, you'll see the ratio image that clearly identifies something as unusual in the scene. The bottom left is a little bit zoomed in and a better stretch of that. And on the right is a blink between the old and new data set identifying the crater. And in many cases, we've been able to resolve craters. The upper left figure shows where we have not been able to resolve them, which is the case for most of the identified features. The lower left and the 2 middle figures show some of the better crater forms that we've been able to find. And then for comparison, on the right are the 2 Grail impact sites, just kind of for context of what those impacts look like versus what these natural ones are looking like. And many times we find more than one of these impact change detections, rather, in one of these temporal pairs. These 2 figures are just an example of how the distribution of the detected changes lie within the scene. The black points represent the low reflectance changes, and the white point on the right figure is where a high reflectance change has occurred. So the count so far, we've examined 106 of these temporal pairs. 77 of those have shown some sort of detectable change. We've got 441 that are in the low reflectance category, 48 in the high reflectance, and we have a total of 491 identified. It doesn't quite add up because there's a couple of them that are unclassified yet. And 66 of those temporal sites, temporal pairs, have had more than one impact feature discovered in it. And out of all 491 features we've identified, 38 of those have discernible crater rims. And just for context, I included a few slides here where they're located. The high reflectance features here, we've been randomly sampling the moon as far as which data to look at. And the next slide is the low reflectance features, which have a lot more of them. And then the third slide of locations is for where we found the cluster of changes where multiple detections have been found in one temporal pair. As far as the sizes of these, on the left we have the ejecta size, and both of these plots are bin to the half-meter scale. On the left is the ejecta diameter, where it's the continuous extent of the detected change within the ratio image, and not including any rays that are seen. And then on the right are the diameters where the craters have been resolved. And in both cases, we're getting close to the limit of the NAC resolution. Anything smaller we will not be able to measure with confidence. So our current implications on this are, out of the nearly 25,000 square kilometers we've looked at, and the maximum temporal window between a pair is 2.5 years. If you extrapolate that to the whole moon, we're estimating about 317,000 impacts on the moon per year that could be detectable with the NACs. And put another way, that's about one impact per 125 square kilometers per year. Numbers like these might help get at some hazard assessments. And based on the resolved craters, depending on the impact velocities and densities, we're estimating impact bolides to, the bolides causing the impacts to be about 1 centimeter to 1 meter in diameter. And finally, implications for the regolith. We've been looking at trying to decide what the differences between these high versus low reflectance features are. And it turns out that most of the low reflectance features appear to be on the shallow slopes, where the high reflectance are on the more steep slopes, although we need the NAC DEMs to confirm that. But if that's true, that implies the shallower slopes may have a thicker layer of optically mature material, and the steeper slopes may have a thinner layer of optically mature material. And our tentative conclusion is that the low reflectance changes do not excavate below the optically mature material, and that low reflectance is likely due to a porosity change relative to what the surface was before the impact. And I went pretty fast, but I'm done.
Great, thank you so much. So actually, this is a fantastic study, and really is going to constrain the Earth-Moon impact rates over the last couple of years. There's one question from Rick Elphick, who says, "Sorry, I may have missed it. Was LROC able to image the location of the most recent impact event seen by the Marshall folks?"
The answer is yes. We have started imaging it. We have another pair coming down. Actually, it came down last week. We haven't looked at it. We've seen a couple of very small changes, but we have yet to fully study the whole area and tie it together with what they saw.
Okay, great. I actually had a quick question, and I was curious if there are any plans to correlate some of this data or some of these studies back to the Lunar Orbiter data set that's being reinvented, so to speak, and whether or not you have plans to look at that over the last 40 years as opposed to the last 20 years and see if there's a change in impact rates.
We do not have a plan to set out to look at that, to compare it with the Lunar Orbiter data. I know Ingrid Dubar's team down at U of A has been comparing it with the Apollo panoramic data, which is a similar time frame, but they've been having difficulty doing it, and there's also a lot of effort that would be needed to do the Lunar Orbiter co-registration. Not to say that it can't be done, if it should be, but we do plan on doing it. We're looking at the NAC to NAC data.
Okay, great. Carly Peters says, for some of the low reflectance IDs, could it be due to impact or contamination? And a related question, is there any size relation with the bright and dark craters that you see?
Well, for the first part of it, as far as the contamination based on the impactor, I can't rule out that that's not a possibility, but we just don't have the data to tell without getting a sample from that site or witnessing the bolide before it impacts. What was the second part of the question? Is there any size?
Is there size relation between the bright and dark, the light and?
There's not. They are pretty much equally distributed within that histogram.
Okay. Bill Baki asks, have you compared your results to the bolide disruptions in the Earth's atmosphere after Brown et al. 2002?
We have not, but that is one aspect that we plan on looking at.
Okay. Since you ended early, we're going to take a few more questions, which is always fantastic. John Keller asks, do the cluster discoveries imply a breakup of the objects nearby or swarms? Do you see any evidence of that?
It's certainly possible. The one thing I might say, just based off of looking at the data recently, is the cluster of impacts tend to occur when there's a larger temporal window, such as 2.5-year windows between the old and new pairs. That they tend to have more impacts within them as opposed to one that's only a 6-month temporal window. That could imply that these are not grouped events from a single breakup event.
Okay. Michael from UCLA says, the freshly excavated material seems to be so bright that it saturates the current exposure settings of the camera. Have any of these impacts been reobserved with different exposures to measure how bright this material is?
The first part of that is not true. We have not saturated the pixels yet as far as imaging any of these bright features. Have any of the impacts reobserved differently? No, we have not, but we do plan on re-imaging some of these just to see how much degradation has occurred with the reflectance value of that new material.
Okay. Great. Well, thank you all so much. If there are any further questions, go ahead and take them